Hello everyone, welcome to the presentation of a physics-based Simscape compact silicon carbide power MOSFET model with temperature scaling. I am Abu Shahid Muhammad Khalid Hassan and my co-authors are MD Maksudul Hussain and Dr. H. Allen Mathur. We are from the MSCAD lab at University of Arkansas Fayetteville. Let's look on the outline. First we will have the overview of the compact modeling. Then we will discuss silicon carbide power MOSFET model. After that, we will introduce Simscape implementation, and then we will discuss model validation and parameter extraction. After that, we will have application simulation, and at last, a brief conclusion. So why we need compact modeling? The circuits we use may have lots of elements. The model for each element contains many equations. The behavior of the whole circuit may be needed at many points. All implicit equations might need to be solved repeatedly for each point. Therefore, we need a compact model which should be simple yet accurate description of the terminal characteristics of a semiconductor device should be represented as a function of the terminal bias. It is a device model that shares most of the computation time. We all know that numerical solution requires equations at very large number of geometry points inside the device. Therefore, although it is the most accurate yet not applicable for circuit or system level simulation. Now let's look on the different types of compact modeling. The physical models are based on device physics, parameters have physical significance, and the modeling is technology independent. Usually equations are non-physical in empirical models. Parameters are only exponent and coefficient, there is no physical meaning. It requires multiple measurements to develop equations. For lookup table models, computer looks up instead of calculating. The accuracy depends on the availability of large data points. The simulator needs to interpolate the in-between points of the loss table, which not only adds to the computational burden of the simulator but also can introduce error in the estimation. Therefore, a compact model should be simple yet accurate. If there is a physical basis, it is a great advantage. It should be computationally efficient, scalable to geometry and temperature, and there should be a simple parameter extracting sequence. Silicon carbide has gained popularity recently because of its superior device characteristics. A higher critical breakdown field, which means a voltage rating can be maintained while still reducing the thickness of the device. A wider band gap leading to lower leakage current at relatively high temperatures. A higher thermal conductivity supports a higher current density. Silicon carbide devices can operate at high frequencies because of higher saturation velocity. And why Simscape is important, it allows us to design physical component models based on physical connections that directly integrate with block diagrams and other modeling paradigms. It allows us to design custom component models using the MATLAB-based Simscape language. Also, it allows us text-based authoring. We can deploy models to the simulation environments, including hardware-in-the-loop systems, and Simscape also supports C code generation. Based on the analytical model published previously, there have been models in Verilog A, MAST, and LTSpice. We have implemented the silicon carbide model in Simscape in this paper, which features accurate description of channel and diff region, nonlinear capacitances, internal charges, gradual transition from linear to saturation region, temperature scaling, and a datasheet-driven parameter extraction procedure. Let's look on the structure of the silicon carbide power MOSFET model used in this paper. The device has three external terminals, gate, drain, source, and two internal nodes, SIDI. The channel current ICH consists of two components, IMOS-L and IMOS-H, which corresponds to low and high current region. The gate-to-source capacitance is modeled with parameter CGS, which is combination of gate-to-source overlap capacitance and metallization capacitance. The drain-to-source capacitance CDS, which depends on the depletion thickness variation due to the change in bias voltages. The gate-to-drain capacitance CGD is the series combination of oxide capacitance COX and gate-to-drain depletion capacitance CGD dip. Typically, the effect of source resistance and drift resistance are not very prominent in the low voltage devices, but in power devices the effect of source resistance and drift resistance can be neglected, and without internal nodes the effect cannot be described accurately. Now let's look on the model parameters. VTX is threshold voltage parameter. PPF models the soft transition between linear and saturation region which arises due to large interface traps. The high transverse electric field effect is modeled with θx, while KFX and KPX are conductance parameter for linear and saturation region respectively. CDS is drain source capacitance constant part, while M is junction grading coefficient. COX denotes gate oxide capacitance and CGS refers to gate source constant capacitance. RD is the drift region resistance parameter, AGD is the estimated gate drain area, and ND is the drift region doping. The equations are listed in the right side of the slide. Now let's look on the temperature-dependent parameters. The Simscape model is capable to perform temperature-dependent simulations. T denotes the desired temperature and TR denotes the room temperature, which is set as 25 degrees Celsius. The parameters with an extra T in the subscript are the temperature-dependent parameters which need to be used in case of high temperatures. Here the 6 parameters in the table are temperature-dependent version of the parameters we discussed in the previous slide. So for first 4 of them have temperature exponent, and the bottom 2 have linear dependence on the temperature difference. Also we have the temperature dependent bulk mobility parameter in the lower right corner of the slide. For Simscape implementation, the different components, that is ICH, CDS, CGS of equivalent circuit of the model has been implemented in Simscape language individually. In Simscape, a component consists of inputs, nodes, variables, parameters, function, and equation sections. The input section defines the voltage or current dependency of the component on different nodes. The parameter denote fixed values which can be even accessible after developing the model component, while variable can change their value during each time step of MATLAB simulation. The function section calculates the parameters which depend upon other parameters. The double equal operand used in equation section establishes continuous mathematical equivalence between the left and right hand side expressions. This signifies that the equation represents a symmetric mathematical connection between the left and right hand operands rather than assignment. Throughout the simulation, this equation is assessed on a regular basis. For example, the two equations in the bottom has the same meaning in equation sections in Simscape language. Figure shows comparison between Simscape and measured data for different CV curves, CISS, COSS, and CRSS. Good agreement between experimental and simulated data has been noticed here in capacitance versus voltage characteristics. A datasheet-driven approach is adopted here to extract the relevant parameters. Also, the parameters for off-the-shelf device can be extracted with these methods. The extraction procedure starts with the capacitance parameters, the oxide capacitance COX, the gate drain overlap area AGD, and the body diode emission coefficient ND is extracted from the CRSS curve as shown in the figure, while the drain to source capacitance CDS at zero bias and the junction grading coefficient M are obtained from the COSS curve. Eventually, the gate to source capacitance CGS is extracted from the CISS curve. Good fit between experimental and simulated data has been noticed here in the device transfer characteristics and the DC output characteristics. The low current gain KPL and the low threshold voltage VTL are extracted from lower part of the transfer curve as shown in figure in the left, while high current gain KPH and the high threshold voltage VTH and the mobility reduction parameter θH from the higher part of the same curve. Then the other two current gain parameters KFL for low current region, kFH for high current region, and the transition parameter PVF is obtained from the output characteristics curve as shown in figure in the right. Also, the Simscape model has performed soundly at high temperature. Figure shows comparison between Simscape and measure data for the pre-device for IDVGS and IDVDS for 150 degrees Celsius. For dynamic validation, a double pulse test has been implemented using the same Cree MOSFET. The circuit diagram of the DPT test for the Cree device is shown in the figure in the middle. An inductor of 320 microhenry is used as the inductive load, and the DC voltage source is set to 410 volt. The pulse generator is used to generate the required pulses with magnitude of -5 volt to 20 volt. The Cree MOSFET, which is used as the DUT, is connected to the V pulse through the resistor RG. Another Cree MOSFET is used in the off mode as the top device, which is connected in the parallel to the load. Comparison between Simscape simulation and measure data for the DP test is shown in figure 7. A and B show the turn off and turn on of the drain source voltage VDS of the DUT respectively, while C and D show the turn off and turn on of the drain source current IDS of the DUT respectively. The parasitic in the measure data was tried to be adjusted as much as possible. The switching loss comparison for the DPT test is shown in the table. The turn-off switching energy E on is much less than the turn-on switching energy E on as expected. The DPT circuit is used to simulate the model performance at different gate voltages. A shows the gate voltage VGS to the DUT, which is varied from 4 volt to 5.5 volt with step size of 0.5 volt. The response of the Simscape model is plotted as the drain to source current IDS in figure B and the drain to source voltage VDS in figure C. This type of simulation can be helpful for multi-level active gate driver design. The simulations are run with Intel Core i7 3.4 GHz processor and 16 GB installed memory. Both the static and dynamic simulations are done using the backward Euler solver, which uses sparse linear algebra to solve the simulation in MATLAB Simulink. The delay memory budget and filtering time constant is set to 1024 KB and 0.001 respectively. The simulation time of the static and dynamic simulations estimated using the Simulink profiler, and the results are presented in the table. The figure in the left shows a circuit diagram of the multi-level inverter, which is designed to simulate using the Simscape model. 8 MOSFETs M1 to M8 have been used to design the multi-level inverter. An inductive load of 1.5 millihenry is utilized with 50 ohm series resistance. Both of the DC source VDC are kept to 100 volt. The gate control signal for the 8 MOSFETs is plotted in the middle. The output voltage of the multi-level inverter with Simscape model is presented in figure A. Some parasitics were included in the multi-level inverter to simulate the ringing, which can be noticed clearly in the zoomed-in version of figure B and C. The experimental results using the Cree power MOSFET has shown that the model produces good fit for the DC transfer characteristics, DC output characteristics, as well as for the CV characteristics. The high temperature equations are added to simulate the model in harsh conditions. The temperature voltage is reduced in high temperature and the drain source current increased as expected. The DPT test also shows good agreement with Simscape simulation, which proves dynamic validation. The silicon carbide model has responded well in dynamic simulation with different gate voltages. The Simscape model has worked successfully in different circuits with built-in control systems in MATLAB. simulink environment. These are the references which have been used in this presentation. Thank you very much for your attention. Looking forward to see you in the ECCE 2022.